Snell's law, also known as the law of refraction, also known as Snell's law. So here's Snell's law. It says that light's index of refraction in its incident medium multiplied by the sine of its angle of incidence is equal to its index of refraction in the medium through which it refracts multiplied by the sine of its angle of refraction. The index of refraction is defined to be the speed of light in vacuum divided by the speed of light in some medium. The subscript I means the quantity it's attached to is referring to the incident medium, and the subscript R means the quantity it's attached to is referring to the refractive medium. Warning: I make two simplifying assumptions in this video. We've already reached our first assumption, and that is the length scales of the media in this derivation will be much longer than the wavelength of the light. This means we can approximate the electromagnetic radiation as rays as opposed to waves. Not only that, but locally we can say these light rays correspond to plane waves. So a plane wave is a wave whose surfaces of constant phase or wave fronts are infinite parallel planes. And of course these waves don't exist, but under our assumption they resemble the electromagnetic radiation locally. And if you don't know what I mean when I say phase, let me try to explain. So here's a portion of a wave, one wavelength to be exact. And if we're talking specifically about electromagnetic radiation, then it is the fluctuation in magnitude and direction of the electric and magnetic fields that give rise to this pattern. And so at any given instant, since this pattern is cyclical, it's repeating, you're going to be somewhere along in this pattern, say here for example. And so this would be what you refer to as your phase, which is usually measured relative to some reference point, which you could say is here. And this transverse wave I drew is of course just a mathematical representation of the fluctuation in direction and magnitude of the electric field, for example, in an electromagnetic radiation. You'd also have the magnetic field fluctuating in direction and magnitude orthogonal to the electric field's fluctuation. So just to clarify that, that's what's going on here. This could be the electric field and this is the magnetic field, and so you have electromagnetic radiation coming at you like this. But if I move like this, perpendicular to the direction of motion, I'm not changing my phase. So really I should only be moving my hands as I move forward. So, like I said, moving in this plane that's perpendicular to the direction of motion, so this plane where I'm going like this, the phase is constant. Now I'm changing the phase, now I'm not. Now I'm changing the phase, now I'm not. Okay? Okay, so we have a couple of light rays corresponding to a plane wave in an incident medium. And you can think of these rays as being points on the plane wave that only are given dimension by the fact that they're propagating through space and time. So, here I've labeled the angle of incidence, which is measured relative to this dotted line I've drawn, which is, by definition, by how I've drawn it, perpendicular to the interface, or where the two media intersect. So there's your angle of incidence and there's your angle of refraction. And here's your incident medium and here's the medium through which the light refracts. Or the labels for the two. Alright, so now what am I going to do? Well, it's time to do some basic geometry. So I'm going to label some points, right? I'm going to put a point right there. Label that A. Guess what? I'm going to put a point right there. Yeah, I'm going to put a point there. I'm going to label that B. And you know what? I think I'm going to put a point right there, label it C. and I'm going to put a point right here, label it D. And why have I done this? Well, check this out. I'm going to connect the dots. Whoa, 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 whoa. I'm going to connect the dots, alright? Now, I'm intentionally drawing these lines so that they're perpendicular to the direction of propagation. What does that mean? Oh, constant phase. Isn't that convenient? We're going to learn how convenient that is in a little bit. Alright, so there you have it. Now I have a couple of right triangles, if you don't see them already. I'm going to label this, that's 90 degrees right there. This is 90 degrees right here. That's theta I. And this dotted line, remember, creates a right angle with the interface. So if that's theta I, this angle in this triangle here must be 90 minus theta I. I'll label that 90 minus theta I. It's going to be hard to see, I guess. And so we all know this, that the sum of the angles in any triangle equals 180 degrees. But if you don't believe me, I guess I'll prove that now. Okay, so I've drawn an arbitrary triangle with 3 angles labeled A, B, and C. And I've drawn a line that runs tangent to this vertex and is also parallel to the base of the triangle. So what you may notice is that what we have here is a couple of parallel lines with a couple of transversals running through them. And so what that does is it creates what are called alternate interior angles. So interior meaning the angles are between the 2 parallel lines, and alternate meaning they're on opposite sides of the transversal. So for example, we have angle C here. It's between the parallel lines, and so on the other side of the transversal would also be angle C. And the same goes for B. We have B over here. Alternate interior angles. And so as you can clearly see, A plus B plus C equals 180 by definition of the degree unit. You can quickly see how alternate interior angles are equal by observing that if you look at the image that you've drawn of 2 parallel lines being intersected by a transversal, if you turn your head upside down, it's essentially the exact same image. In addition, you could say you start with 2 parallel lines with a transversal that runs perpendicular to both. And once you start tilting it, making the angle no longer 90 degrees, the angle of intersection of the 2 parallel lines, you could see how it would affect the alternate interior angles in the same way. Alright, so now we know there's 180 degrees in a triangle. So back to this 90 minus theta I. Okay, we're going to do some simple addition now. Watch out. We got 90 degrees here. We got 90 minus theta I here. What do we need to get to 180 degrees? That's right. Theta I goes right here, baby. Alright, now look at this over here. We got this dotted line that we said is perpendicular to the interface. And so we know that the sum of this angle outside of the triangle and this angle here in the triangle must be 90 degrees. So then, and this angle here is theta r, remember. So then this must be 90 minus theta r. And therefore, to get to 180 degrees, this over here must be theta r. We have now reached our second assumption, which is that both media are linear. And one of the characteristics of linear media by definition is that they do not change the frequency of light. This assumption is very important because, of course, this ray of light reaches the refractive medium prior to this ray of light. And therefore, if this refractive medium were able to change its frequency, then moving in the direction perpendicular to the direction of propagation may no longer mean that you are in a zone of constant phase. Okay, now I'm going to make a pretty big claim here, so buckle your seatbelts. My claim is that it takes the same amount of time to get from point B to point C as it does to get from point A to point D. You might be thinking, well, it looks like from point B to point C is a larger distance than from point A to point D, and you'd be right. And that's because the speed of light in its incident medium is greater than it is in its refractive medium. Or more specifically, its phase velocity is greater in the incident medium than it is in the refractive medium. And that is specifically referring to any phase in the wave itself, the speed at which that phase moves, whether it be the crest or the trough or somewhere in between. So the phase velocity can change and the wavelength can change, but the frequency cannot. Okay, so point A and point B are at the same phase because I've drawn a line connecting them that's perpendicular to the direction of propagation of the plane wave. The same is true for point C and point D. Now, we have the same starting point regarding phase and the same ending point regarding phase and the same rate of change from point B to C as is the case from point A to D. So you have the same starting point, the same ending point, the same rate of change. It must be true that you've done so in the same amount of time. Therefore, the time it takes to get from point B to C is the same as the time it takes to get from point A to D. It's also important to think about why light refracts at all. So you can, let's see, okay, so these two light rays are components of a plane wave that can describe the radiation locally. So you can think of this light ray as, say, for example, the right side of a car. So like, think of point A as the right front tire. Point B can be the left front tire. Now point A, this right front tire got stuck in mud, and it's going to get stuck or move more slowly than this left front tire that's on a paved road. So what happens is you begin to pivot as one side moves more quickly than the other. That's one way to think about why refraction occurs. This side's moving more quickly than this side, so you get some of this going on. Basically, the radiation has to move at two different velocities at the same time while remaining continuous. It won't break apart, and you solve that by bending it. Okay, so now it's time for some plug and chug. So we know that T AD, that is the time it takes to get from point A to point D, is equal to TBC, which is the time it takes to get from point B to point C. Let's also note that the line segment BC is equal to the sine of theta I multiplied by the line segment AC. Remember SOHCAHTOA, sine is opposite over hypotenuse. In this case, the opposite side from theta I is BC. The hypotenuse is AC, so you need to multiply by AC to get back to BC. The same is true for AD, which is the opposite side from theta R. So you take the sine of theta R multiplied by AC, which is the hypotenuse of this right triangle, to get AD. I've now expressed the time it takes to get from point A to point D as the distance between points A and D divided by the phase velocity in the refracted medium, because that's the medium through which you travel to get from point A to point D. And then similarly, I have the time it takes to get from point B to point C given by the distance between the 2 points divided by the phase velocity in the incident medium, which is symbolized by V sub I, and also that's the medium through which you travel to get from point B to point C. So now all I did is I plugged in the values for BC and AD, that is the line segments between the two respective points, and I've crossed out the line segment AC on both sides of the equation, and I've multiplied both sides by C because I can do that. And so now I have Snell's law. QED, square that's been filled in, got him. And you know what? Yeet!